Hello and welcome to this video for Chemistry 30 in the equilibrium unit. What we are going to look at in this video is something called Le Chatelier's principle. So Le Chatelier studied systems that were at equilibrium and then looked at what happened when you disturbed that system. Okay, so you are changing a property in the system, and the system is going to adjust to oppose the change. So we're starting with a system at equilibrium. The system is then going to shift. Now, what does that mean by shifting?
Please excuse this interruption. Drama Club is happening in the theater right now. All Drama Club members, please head to the theater now. Thank you.
Sorry. If it's shifting to the product side of the reaction, this means the forward process is speeding up. The forward rate is increasing. So that means the reactants are reacting a little bit more, which is decreasing their concentration, and the products are increasing in concentration because they're being produced. However, I could also have a reaction where it shifts to the reactants. Now, if it's shifting to the reactant side of the equation, this means the reverse process, its rate is increasing. Okay, so this would mean my products are reacting together to get used up to produce more reactant because it's trying to either replace what was removed, or it's shifting that way. There's a few different reasons why it's going to shift, and that's what we'll look at in this lesson. So here are the stresses. We call them stresses that we can apply to change the system. We can change the concentration by adding or removing something. We can change the temperature by heating or cooling the system, or adding or removing energy. We can change the pressure and therefore the volume. When I increase the pressure, the volume is going to decrease and vice versa. It's an inverse relationship, okay? So we're going to start with concentration changes. Let's say I am increasing the concentration. Remember, square brackets represents concentration. So if I am increasing the concentration of something, that means that I am adding something, okay? I am adding either a reactant or a product. And when I add something or increase the concentration of something, it is going to shift to the opposite side. Okay, so if I add a product, it'll shift to the reactant side. If I add a reactant, it'll shift to the product side. The reason this is happening is because when you add more of that substance, there's more of it to react. So it gets used up a little bit to make more of the other side. Okay, if I decrease the concentration of something, and this is done by removing something, it is going to shift to the same side because it's trying to replace what was taken out. Now, you can indirectly remove something by actually adding something, okay? And so what I mean is you could have a neutralization process. So if your system has hydronium ions in it, and you add hydroxide ions in it, that is going to remove the hydronium ions. And vice versa, if you were to have hydroxide ions and add hydronium ions, it would remove the hydroxide ions, okay? The second way you can remove something is by forming a precipitate. Remember, a precipitate is an insoluble ionic compound. Okay, and so when your system starts with these free ions, so let's say I have silver ions in my system, and what happens is I add chloride ions, they're going to form a precipitate. And so that's going to remove the silver ions from the system as the precipitate silver chloride is produced. Okay? So forming a precipitate, again, removes ions that were once soluble because they become insoluble with whatever has been added. Now next, we're going to look at an example. This is known as the Haber-Bosch process. So in the Haber-Bosch process, we have the formation of ammonia gas by reacting nitrogen and hydrogen. We're going to do just kind of a really straightforward example here where we're told directly, I am increasing the concentration of nitrogen. So I go to my equilibrium process, I increase the nitrogen, which means I'm adding nitrogen. So it's going to shift to the opposite side, okay? Whenever you add something, it shifts to the opposite side. So this will cause the reaction to shift to the products. Now, what that means is that I have more reactants to react, so they're going to go down a little bit after I've added some nitrogen, where my product is going to increase. And we're going to look graphically at what that looks like, okay? So when you add something, it shifts to the opposite side. Next, I'm going to add some ammonia. So I'm going to increase the concentration of the ammonia because I'm adding it. What's then going to happen is it's going to shift to the reactant side. So when I add product, it shifts to the opposite side, which is the reactant side. Sometimes you'll also hear these shifts being told to the left or to the right. So to the products is to the right, to the reactants is to the left. Now in the last example, we are removing ammonia, okay? When you decrease the concentration by removing something, it's going to shift to the same side because it's trying to replace what was removed. So if I remove a product, it's going to shift to the products, okay? Now the last thing to understand is that when you change the concentration, it has no effect on the value of Kc. Kc we learned about in the last lesson, the equilibrium constant, the relative ratio of products to reactants. That does not change when you add or remove something. Next, we'll look at temperature. When you have a temperature change, you want to understand what type of reaction you have. Is it an endothermic reaction? And if it is, you could be given delta H from the thermo unit would be positive. This means energy is a reactant. If you're told you have an exothermic reaction or you're given delta H and it's negative, energy is a product. Now energy, we're going to treat it just like it's another reactant or product. So if I cool it, that means I'm removing energy, it's going to shift to the same side. And then if I heat it, that means I'm adding energy. Whenever you add something, it shifts to the opposite side. So again, it depends on if you're adding or removing and which side of the equation the energy is on. Now, this is the only stress that will change Kc. If my reaction shifts to the product side, that means the concentration of the products go up and the concentration of the reactants go down. That's going to make the value of Kc increase. If instead it shifts to the reactant side, the products are therefore going down to make reactants which go up, and now my Kc is going to get smaller. Okay, let's look at an example of this. So the Haber-Bosch process is exothermic. Energy is a product. So if I heat the system, I'm adding a product, so it's going to again shift to the opposite side. It's going to shift to the reactants. Again, when you add something, it always shifts to the opposite side. Now instead, if I cool this system, I am removing a product. I'm removing the energy. So again, when you remove something, it shifts to the same side. So it's going to shift to the products. Okay, so treat energy like a substance in the reaction. And again, like before, when you add something, it shifts to the opposite side. When you remove something, it shifts to the same side. Next, we're going to look at volume and pressure changes, okay? Now, if I increase the pressure of my system, my volume is going to decrease. That's going to cause an immediate spike in everything that is a gas in your reaction vessel. So what I mean is if I have a certain gas given in this volume, and I have a few particles and then I look at a 1 liter section, because concentration is looking at how many particles there are per 1 liter section. Let's say I'm starting with 1 mole per this liter section. If I decrease the volume and give less space for the particles to move around in, they are going to have the same number of particles, but they're going to get closer together. So now in that 1 liter section, I have 2 moles per liter. Okay? So when you decrease the volume because you've increased the pressure, the concentration of everything initially is going to go through a spike up. If you were to increase the volume, everything is going to go through a spike down. Then will come the shift, only if there is an imbalance in the number of moles of gas on the reactant versus the product side. If I look at this reaction, I have 1 moles of nitrogen gas, 3 moles of hydrogen gas, so in total, I have 4 moles of gas on the reactant side and only 2 moles of gas on the product side. If there's a different number of moles on each side, when you decrease the volume, it will shift to the side that has fewer moles of gas. Okay? When you decrease the volume, it'll shift to the side that has fewer moles of gas. You can think of it as there's less space for the gas to move around, so it's going to shift to the side that wants to take up less space, which is the side that has less moles. And then if you increase the volume, it's going to shift to the side with more moles because now you have more space for it to move around in. And if you are changing the volume and the moles are equal, there will be no shift. There will still be that initial spike where all the concentrations go up or down depending on if you're increasing or decreasing the volume, but there will be no shift to the reactant or product side. I kind of went through this last example quickly. This was just showing again that if I were to decrease the volume, it would shift to the ammonia side in this example because that's the side that has less moles. Okay, when you increase the volume, it goes to the side with more moles. If the moles are the same, then there is no shift. Okay, this again is not going to affect our value of Kc. Now, one thing I want to add here before I move on is you can add a catalyst or an inert gas. Some common inert gases, inert means non-reactive, are your noble gases. So something like helium, okay? When you add a catalyst or an inert gas, absolutely nothing happens. There is no spike, there is no shift, nothing happens at all. Okay, your system is already at equilibrium. This is not a stress being applied to it. Now, sometimes your system can have colors, different colors for the reactants and the products. Then whenever it shifts to that side, it's going to change to that side's color. So for example, let's say we have the following equilibrium system. We have chromate ions, which are yellow. They're reacting with hydronium to make dichromate ions, which are orange, and water is a product. Now, this question kind of seems a little tough because it's talking about adding crystals of things, okay? Ionic compounds always start as a crystal. When you put them in water, if they're soluble, which group 1 ionic compounds always are, sodium, potassium being group 1 ions, these will dissociate and split into their ions. Okay, so when I'm adding a crystal of sodium chromate, what I'm essentially doing is increasing the concentration of the chromate. The sodium ions are just a spectator ion. They're not doing anything, but the chromate is in the reaction. I'm adding some chromate. So it is going to then shift to the opposite side, which is the dichromate side. So it's going to shift to the products, and the products are orange. Okay? If I add a crystal of potassium dichromate, again, the potassium is just a spectator ion. I am essentially increasing the concentration of the dichromate. Okay? The instantaneous thing that's happening is I'm increasing the concentration of dichromate. The shift then that will take place is it'll shift to the opposite side, it'll shift to the reactant side, and the reactants are yellow. Next, I'm adding a few drops of concentrated acid. That means I'm increasing the concentration of hydronium ions. Hydronium ions are a reactant. So if I increase the concentration of a reactant, it shifts to the product side, which again is orange. In D, we are removing water. Water is a substance in this reaction. So I am physically decreasing the concentration of the water. I am removing the water. When we remove something, it shifts to the same side to replace it. So this is also going to shift to the product and turn orange. Now the last thing we're doing is adding sodium hydroxide. Again, crystals, because it's not yet in water. Ionic compounds before they're in water always start as a solid. When I add them to this solution, it will dissociate into sodium ions and hydroxide ions. Neither of those are part of the equilibrium system, but we talked about this. Hydroxide ions are the indirect removal of hydronium ions because it is neutralizing them. So by neutralizing or removing the hydronium ions, the reaction will therefore shift to the reactant side and turn yellow. Okay? Let's look at a sample diploma question. We have these two reactions taking place in blood, and we are increasing the concentration of CO2. When I increase the concentration of CO2, that's going to make the first equation shift to the right, or to the product side, which makes the hydrogen carbonate increase. Hydrogen carbonate, or carbonic acid, is in the second reaction, so it is now in a higher concentration. So it's going to make the second equation also shift to the right, which will again increase the hydrogen carbonate ions. Okay, so the answer for this would be C. The first equation is shifting to the right, and that causes the concentration of the HCO3 to increase. Now, the last thing we have to look at is looking graphically at what happens during our shifts. Okay, so you're going to be given a graph and either asked to draw it, or you're given a graph drawn and you're asked to identify what shifts are taking place. So we'll look at the Haber-Bosch process again. I'm starting with everything at equilibrium. So everything starts as a flat line. This is concentration versus time, right? When equilibrium is established, everything's concentration is constant. I'm going to, at time A, add hydrogen gas. That's going to cause an instantaneous spike or jump in hydrogen gas. That is not my shift though, okay? That is just because I've added hydrogen, it spikes up instantaneously. Then it's going to go through a shift, and the shifting process will be seen as a curved line because it doesn't instantaneously change, it slowly reacts, so it slowly increases or decreases. Okay? If I'm adding hydrogen gas, which is a reactant, it's going to shift to the product side. So what that means is going to happen is the concentration of my product is going to go up. But in order for that to happen, my reactants have to get used up a little bit. Okay? So you will see ammonia going up in a curved line and then plateauing again, reaching equilibrium. Then nitrogen and hydrogen go down in a curved line and reach equilibrium again. Okay? So that initial spike, if you are trying to identify based on being given a diagram what happened here, if one thing spikes up or down, that means you've added or removed that one thing. Okay? Next, we're going to add an inert gas or catalyst. Nothing happens. Flat line. Okay? Nothing is shifting. Nothing is being added or removed. There's no change. Next, we are going to decrease the volume. Now, remember we said when we decrease the volume, instantaneously everything's concentration is going to spike. That's how you can recognize a volume change from a graph. If everything spikes up, you have decreased the volume. If everything spikes down, you have increased the volume. Okay? Then it will shift to the side with more moles. If each side moles were equal, after the spike, it would be flat, meaning no shift, okay? But if they're unequal, which they are, it's going to shift to the side again. When I decrease the volume, it'll shift to the side with less moles. There's 2 moles of ammonia product versus 4 moles of reactant. So it again is going to shift to the product side, making the products go up in a slow curved line, and my reactants get used up a little bit and go down in a slow curved line. Okay, so when everything spikes, that's a volume change. The last change we're going to apply is energy. Now, energy is not one of the 3 substances on our graph. So when I add energy, none of them are going to initially spike. I'm not adding or removing anything. I'm not changing the volume. It's only going to have a shift. So when I increase energy, which in this case is a product, it's going to shift to the opposite side, which is to the reactants. Now, when it shifts to the reactant side, that means my reactants are slowly going to increase, and my product is going to get used up a little bit to make more reactants. So you'll see the ammonia slowly go down and then flatten out, and my 2 reactants will both slowly increase and then flatten out. Okay? So that is the lesson on Le Chatelier's principle, looking at it graphically as well as predicting which direction your system shifts to. I hope this lesson helps.